In this video, we will discuss regression. In some cases, two variables are related in a deterministic way, meaning that given a value for one variable, the value of the other variable is exactly determined without any error, as in the equation y equals 2.54x for converting a distance x from inches to centimeters. Such equations are considered in algebra courses, but statistics courses focus on probabilistic models, which are equations with a variable that is not determined completely by the other variable. For example, the height of a child cannot be determined completely by the height of the father and/or mother. Sir Francis Galton studied the phenomenon of heredity and showed that when tall or short couples have children, the heights of those children tend to regress or revert to the more typical mean height for people of the same gender. We continue to use Galton's regression terminology, even though our data do not involve the same height phenomena studied by Galton. Given a collection of paired sample data, the regression line, or line of best fit, or least squares line, is the straight line that best fits the scatter plot of the data. The specific criterion for the best fitting straight line is the least squares property described later on. The regression equation, y hat equals b naught plus b1x, algebraically describes the regression line. The regression equation expresses a relationship between x, called the explanatory variable, predictor variable, or independent variable, and y hat, called the response variable or dependent variable. In statistics, the typical equation of a straight line y equals mx plus b is expressed in the form y hat equals b naught plus b1x, where b naught is the y-intercept and b1 is the slope. The values of the slope b1 and y-intercept b naught can be easily found by using any one of the many computer programs and calculators designed to provide those values, or with manual calculations. Notation for the equation of a regression line. The y-intercept of the regression equation has sample statistic b naught and population parameter beta naught. The slope of the regression equation has statistic b1 and population parameter beta 1. The equation of the regression line is y hat equals b naught plus b1x for the statistic, and y equals b naught plus beta naught plus beta 1x for the parameter. The requirements. First, the sample of paired XY data is a random sample of quantitative data. Second, the visual examination of the scatter plot shows that the points approximate a straight line pattern. Third, outliers can have a strong effect on the regression equation, so remove any outliers if they are known to be errors. Consider the effects of any outliers that are not known errors. Requirements 2 and 3 are simplified attempts at checking these formal requirements for regression analysis. For each fixed value of x, the corresponding values of y have a normal distribution. For the different fixed values of x, the distribution of the corresponding y values all have the same standard deviation. This is violated if part of the scatter plot shows points very close to the regression line, while another portion of the scatter plot shows points much farther away from the regression line. And for different fixed values of x, the distribution of the corresponding y values have means that lie along the same straight line. The methods of this section are not seriously affected if departures from normal distributions and equal standard deviations are not too extreme. Formulas for finding the slope and y-intercept in the regression equation. The slope is b1 equals r times s sub y over s sub x, where r is the linear correlation coefficient, s sub y is the standard deviation of the y values, and s sub x is the standard deviation of the x values. The y-intercept, b naught, is equal to y bar minus b1x bar, where y bar is the mean of sample y values and x bar is the mean of sample x values. The slope b1 and y-intercept b naught can also be found using the following formulas that are useful for manual calculations or writing computer programs. b1 equals n times sigma xy minus sigma x times sigma y over n times sigma x squared minus sigma x quantity squared. and B naught equals sigma y times sigma x squared minus sigma x times sigma xy over n times sigma x squared minus sigma x quantity squared. Rounding the slope and the y-intercept. Round B1 and B naught to 3 significant digits. It's difficult to provide a simple universal rule for rounding values of B1 and B naught, but this rule will work for most situations in this book. A note on technology. Again, there are many different types of technology you can use to work with regression lines. On page 491, there are 7 different displays from different technologies, including StatDisk, StatCrunch, Excel, and TI calculators. I encourage you to find technology that works for you and learn how to use it. I am focusing here on showing you how to do the manual calculations. Refer to Table 10.1 on page 469. Use the formulas from slide 8 to find the equation of the regression line in which the explanatory variable, or X variable, is chocolate consumption, and the response variable, or Y variable, is the corresponding number of Nobel laureates. Requirement check. The data are assumed to be a simple random sample. The scatter plot of the data set on page 469 shows a pattern of points. The pattern is very roughly a straight line pattern. There are no outliers. The requirements are satisfied. We begin by finding the slope B1 using the first formula on slide 8 with extra digits included for greater accuracy. Remember, R is the linear correlation coefficient, S sub y is the standard deviation of the sample y values, and x is the standard deviation of the sample x values. So B1 equals R times S sub y over S sub x, which is 0.800608 times 10.211601 over 3.279201, which equals 2.493135. After finding the slope, we can now use the second formula on slide 8 to find the y-intercept. B naught equals y bar minus b1 times x bar, which is equal to 11.104348 minus 2.493135 times 5.804348, which is equal to negative 3.366675. After rounding, the slope is b1 equals 2.49, and the y-intercept is b naught equals negative 3.37. We can now express the regression equation as y hat equals negative 3.37 plus 2.49x, where y hat is the predicted Nobel laureate rate and x is the amount of chocolate consumption. Graph the regression equation y hat equals negative 3.37 plus 2.49x on the scatter plot of the chocolate Nobel data, and examine the graph to subjectively determine how well the regression line fits the data. Shown above is the mini-tab display of the scatter plot with the graph of the regression line included. We can see that the regression line fits the points well, but the points are not very close to the line. Regression equations are often useful for predicting the value of one variable, given some specific value of the other variable. When making predictions, we should consider the following. First, bad model. If the regression equation does not appear to be useful for making predictions, don't use the regression equation for making predictions. For bad models, the best predicted value of a variable is simply its sample mean. Second, good model. Use the regression equation for predictions only if the regression line on the scatter plot confirms that the regression line fits the points reasonably well. Third, correlation. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables. And 4, scope. Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. Predicting too far beyond the scope of the available sample data is called extrapolation, and it could result in bad predictions. Here is the strategy for predicting values of y. First, we ask, is the regression equation a good model? That is, the regression line graphed in the scatter plot shows that the line fits the points well. R indicates that there is a linear correlation, and the prediction is not much beyond the scope of the available sample data. If yes, the regression equation is a good model, we substitute the given value of x into the regression equation, y hat equals b naught plus b1x. If no, the regression equation is not a good model. Regardless of the value of x, the best predicted value of y is the value of y bar, the mean of the y values. Use the chocolate Nobel data to predict the Nobel rate for a country with a chocolate consumption of 10 kilograms per capita. The regression line fits the points well, as shown in the previous example. There is a linear correlation between chocolate consumption and Nobel laureates, as shown in the previous section. Because the regression equation y hat equals negative 3.37 plus 2.49x is a good model, substitute x equals 10 into the regression equation to get a predicted Nobel laureate rate of 21.5 Nobel laureates per 10 million people. Predict the IQ score of an adult who is exactly 175 centimeters tall. This is a bad model. Use y bar for predictions. Knowing that there is no correlation between height and IQ score, we know that a regression equation is not a good model, so the best predicted value of IQ score is the mean, which is 100. The key point in these two examples is to use the regression equation for predictions only if it is a good model. If the regression equation is not a good model, use the predicted value of y bar. We can use the regression equation to see the effect on one variable when the other variable changes by some specific amount. In working with two variables related by a regression equation, the marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. The slope b1 in the regression equation represents the marginal change in y that occurs when x changes by 1 unit. Let's consider the 23 pairs of chocolate Nobel data included in table 10.1. These 23 pairs of data result in the regression equation y hat equals negative 3.37 plus 2.49x. The slope of 2.49 tells us that if we increase x, chocolate consumption, by 1 kilogram per capita, the predicted Nobel laureate rate will increase by 2.49 per 10 million people. That is, for every additional 1 kilogram per capita increase in chocolate consumption, we expect the Nobel laureate rate to increase by 2.49 per 10 million people.